Good morning, folks. This is the Computer-Aided Engineering course, and it's also known as Mechanical 4259. The agenda for today is number one, to discuss the syllabus. Of course, after welcoming you back to before even discussing the syllabus, I want to welcome you back to the summer term. So item number one is going to be discuss the syllabus. There is really not much to say there because I already sent you a document saying what you need to know about this course. But anyway, after I discussed the syllabus, we're going to do the first problem, which is going to be from chapter, I believe, chapter 2 of the course. Let me see, chapter 1 of the course, maybe, or chapter 2. And it's your first finite element analysis, probably in CATIA. And then I will talk about the symmetry issues, which is a big thing in this course. Now, as for the syllabus, notice that it says draft May 8, and the reason is that the university gives us 2 weeks to modify and revise the syllabus 2 weeks after the school starts. Now, my plan is not to make any major changes here. The only thing that I may be doing is office numbers for the office information for the GAs and their office hours, etc. So as far as the bulk of the syllabus is concerned, it stays as it is. Okay, my name is Nader Zamani, and here is my office information. And we have a basically 3 50-minute presentations by me, and these are done on Tuesdays and Thursdays. And the first 50 minutes of every lab, you can think about it as being lab/lecture. Okay. Now, the GAs are here. And some of them have already provided me with the office information and office hours. And I'm still waiting for the other 3 to report to me. Notice that some of these are yellow, and these are the people who are going to be running the 8:30 lab on Fridays. Our first lab, by the way, is this coming Friday. And these 2, because there's fewer people in that section, are going to be running the afternoon session on Friday. Now, there is a textbook, but it's not mandatory. And obviously, this Blackboard site should be Bright Space site. So, yep. And these are the textbooks that I'm going to be basically covering this semester. As I said, not mandatory. A lot of the stuff is already on YouTube, and it's up to you. Now, there will be a midterm, which is going to be the Friday during the lab. This is the Friday, June 16, which is immediately before the summer break begins. And the final exam is going to be announced by the registrar. We don't know. And by the way, as far as the midterm is concerned, those of you who are registered in the first lab, you write it in that lab. And obviously, those of you who are in the afternoon lab, registered in the afternoon lab, you're going to be writing it in the afternoon during your lab hour. Now, can I have CATIA on my computer? Can I use it? The answer is, of course you can, but not on the test. On the test, you're going to have one of those computers in front of you in the CEI 2105, the computer lab, and that's where you're going to be doing your work, okay? Now, let's move on. I have a tentative schedule. Notice that the first 6 weeks of the course is on the subject of finite elements. Then you write a midterm, and after you come back from your summer break, the remaining 6 weeks of the course is going to be on some other topic, okay? And the final exam, of course, is not going to be cumulative. After you write your midterm, I mean, you're pretty much done with that subject, okay? All right, now, these are some learning outcomes for the course. I'll leave it like this. You can read it at your own leisure. Now, when it comes to the labs, 10% of your final grade, total course grade, is based on 10 assignments that you're going to be showing to the GAs during the lab, okay? We have 11 labs. One of them, of course, we have 12, but one of them is used for the midterm. So 11 labs, you can miss one, and you can still get your full 10 marks, assuming that you did okay in the remaining 10 labs. Now, the midterm and the final are open book, open notes, open anything you want, no cell phone, no digital form of the book or the notes. You cannot open the PDF files on your computer. If you do open it, we're going to tell you that you can. Delete it, close it, please. You cannot access digital information during the midterm and the final exam. If you don't know what this thing means, please make sure you check with us. Obviously, internet is a digital form of information. Now, the question was, can I use the help, CATIA help? Now, CATIA help is not installed. In order for you to go to CATIA help, obviously you have to go to the browser. And the browser will lead you to where you want to go. The answer is no. During the test, you can't do that. And I'm going to actually do you a favor by saying this, because you're going to be wasting your time. The CATIA help is totally useless for what you need during that limited number of hours for writing the test and the final. Okay? Anything that's confusing, anything you don't understand, let me know. Now remember that the midterm counts for 45%, and the final exam, the remaining 45% of the course, of your total grade. What else do we have? If you miss a lab for a valid reason, and this valid reason, you go to the associate dean, discuss your case with her. If she agrees with your valid reason, we will transfer that weight to the final exam. Okay? I'm sorry. Okay, sorry. No makeup, but the weight of the missing assignment will be transferred to the remaining assignments. Okay, not the final exam. Okay. Now, there won't be any makeups. If you miss the midterm for a valid reason, as assessed by the associate dean, the weight will be transferred to the final exam. And I hope none of you will come to a situation where that can happen, because you're talking about the 90% final exam. That is, not good. What else do we have here? If a fire alarm sounds during a test, the instructor reserves the right to void the test and substitute a new test at a later date. Okay. Attendance. Here's the way the labs work. We don't take attendance, but here's the way things work. You come to your lab, and you come to your lab and let me do the boring 50-minute lecture or presentation, let me call it like that. And then, so between 8:30 and 9:20, I will do my stuff in the lab. If you don't want to hear it, don't come. But when you do come, I don't want any disruptions. In other words, talking to the person next to you so that the other fellow sitting next to you can hear hear me, etc. So I don't want any disruption. If you don't want, come at 9:20 if you wish. At 9:20, your work to be done, that day and in that lab is going to be available to you on Brightspace. Okay, so you open it up, there's something to be done. You try to do it in the next 2 hours and call the GA. The GA is going to come and check your work. I mean, he or she must be convinced that you're putting an honest effort into the work that you're supposed to do. The only caveat is that even if you are a super good in CATIA and you know everything and you finish your work at 9:25, great, go have some coffee, because the GAs are not going to check your work for until 10:20. So basically, I don't know how you can do that, but if somebody is a super person and they can finish their work in 10 minutes, great, go have coffee. So anyway, you get the picture. Basically, you don't have to come until 9:20, but when you do come at 9:20, should you decide to do that, the GAs will not check your work until 10:20. Okay? And they must be convinced that you have put an honest effort. Now, there is no way for us to really know unless the GAs or me start questioning you, what is this thing that you have done? If you cannot answer, that means there's a problem there, right? Okay, good. So let's move on. There are supplemental privileges for this course. If you're a third-year student, and God forbid you do not pass the course and you meet the supplemental privileges criteria, then you're going to be writing in December. Okay. If you're a graduating senior, because there are some of you, maybe 6 or 7 or 8 of you, who are expected to graduate in August and again, or October, I think. Anyway, if you don't pass the course, and I hope that doesn't happen, if it does, then based on the recommendation of the associate dean slash what is called the can't remember, there's a committee who looks at these things. Anyway, I will give you a supplemental, sometime in September or late August, September, etc. Anyway, if you're a graduating senior, we're not going to ask you to come back in December, but you have to pass the course based on your own merits. Okay, people are not going to pass the course just because they're graduating and they didn't put an effort into this course. Okay, you're going to come back and take it next year if needed. All right. Here's some information, important information, but if you want, you can read it. Most of you are probably okay with this. Remember, generally speaking, there are no assignments to be graded in the last 7 days unless it's part of a lab, and this is part of a lab. In labs, in other words, this does not apply to the present course or some of the courses that are also fit in this category. Yeah. Okay, what is it that we have here? Well, there's some important dates. And please make sure you look at these things, read it. This is, they have added a lot of stuff here, which makes the syllabus 17 pages long, I believe. A couple of comments that I'm going to make here. Let me go through this thing. This is all going to be posted. And if there are any issues, please bring it to my attention or discuss it with me. The other thing is that if you are required special accommodation by the student accessibility services, you need to do that within the first, I believe, 2 weeks. I already in that document that I sent you or posted called "What You Need to Do About the Scores," it says that discuss it with me, or if there are any issues, with the midterm, reasonable issues, we have to know that. Okay. Of course, the decision is with the associate dean. However, uh, I don't want you to, to do this thing if it's your, I don't know, brother's wedding on June 16. I understand. Uh, I'll accommodate you, but this has to be sorted out by bring it to my attention in the first 2 weeks, and you need to go to the associate dean for having officially put your case to her. Okay. All right. I'm reasonable, but you should do your homework too. Let me see. The other thing that I'm going to tell you about this course, because I don't want you to be surprised, and that is, this is a fast-paced course. If I were you, I would come to all the lectures or watch the videos. I would do my job in the lab, and I will devote time to, don't let it pile up, time to this course, because it's very easy, very easy. After 3 weeks, you realize, wow, I'm well behind. That is playing with fire. Please don't do that. Okay. All right. That's good. Uh, let's move on. I'm going to close this. Okay. So this is going to be our first problem that we're going to do. We have an object like that made out of steel. The bottom of it is clamped. Clamped means that we are assuming that all the points on this bottom face are fixed and they do not move. Okay? They do not move. And this top face, a force is applied in the indicated direction of the magnitude I think I forgot to mention it here. We're going to make it 1,000 pounds. Okay, I forgot to say what the force is. 1,000 pounds in this direction. Now, a couple of things. This problem may look familiar to you, particularly if you drew it like this. If I draw the spine of this solid object like that, because it's the kind of thing that you did in your stress analysis class. It was a combined loading problem. So you have a bent rod like that, and when you analyze it, this end is clamped, this end is subjected to a load given. So you'll see that when you do it, this member here, or this part of it, the way you did in stress analysis, goes through bending and torsion, but this arm goes only through bending. And based on that, and the Castigliano's energy theorem, you did some calculation and came up with the, for example, deflection of the tip of this bent rod. Now, and later on, we will do this problem using beam elements, the beam theory. But right now, we want to use it. We want to do it with solid elements. Now, what that means is that you take this piece and you break it up into pieces. Now, these pieces can be, for example, a four-noded. These are called the tet element, or tet element, or pyramid-like element, four-noded, or it can be 10-noded. You can only see 9 of them because one of them is hiding in the back. You can't see the other one. So 10-noded, parabolic, tet elements. CATIA calls it octahedral element, okay, tet element. And this is linear 4-noded TET element. Now, these are cheaper. Linear ones are cheaper and less accurate than the parabolic one. In the absence of anything, any other information or any other instruction, you can use linear. Now, just be aware of the fact that if you do this thing for design purposes, you may get results that are not good. It'll give you color if that's the motivation, but results may not be good. Now, a few things that I should tell you about this course. In this course, we will not ordinarily assess the, let me see now, or let me put this, we will not put a lot of emphasis on the accuracy of the results. I mean, obviously, you must have modeled it in a reasonable way. And if you did it and you used a big enough number of elements, that will be reasonable, they will be accurate. But in general, one should do a mesh refinement strategy, mesh convergence strategy, to be convinced that whatever color you're getting, whatever numbers you're getting are actually meaningful, reasonable, okay? Ordinarily, we don't do that, and that's one of the things that's poorly done in industry, because people don't do that. They generate some good-looking colors, some numbers, and they show it to the supervisor. Supervisor might fall into a trap, and they decide to go ahead and make that part, and then they find that it fails. Okay. One of the reasons may be the fact that they did not do any mesh convergence study. Now, the other thing is that we are going to assume in everything that we do in this course, we're going to assume material behaves in a linear elastic way, doesn't go into plasticity, not in this course, okay? And also the deformations are small. So that all the stuff that you learn in your stress analysis course, all the formulas for stresses and strains and things like that are valid. Those were linear or infinitesimal strain formulas that we had, and therefore, just be aware of this fact. Okay. Let me put it this way. If you put, instead of 1,000 pounds here, 10 billion pounds, well, CATIA will run. It'll give you 10 billion miles of or inches of deformation. So we know that that's not going to happen, but CATIA doesn't care. You give it a linear problem, it solves it for you. That's your responsibility to see whether the load that you put actually creates stresses high enough that material is no longer elastic, and therefore basically garbage in, garbage out. Okay. Now, let me quickly go ahead to the next slide and show you, okay, so how do you do this thing in a real situation, assuming the material behaves linearly? Now, notice that if you increase the load here at every point, the stresses will change. And at every point, we have 6 components of stress, 3 normal stresses and 3 shear stresses, okay? Now, if you combine these and find the effective stress or the von Mises stress, which is this expression, then as long as material is ductile, and as long as this effective stress of von Mises stress stays below the yield strength of the material, means that you're okay, you're safe. Another material has stayed linearly elastic, or has stayed elastic, you remove the load, the part is going to go back to its original configuration. But if it exceeds it, then those numbers that you get are totally nonsense, because you have pushed it into the plastic zone, and you're still pretending that it's a linear elastic problem. Okay. Now let me remind you that in your stress analysis course, under the failure section, you dealt with 2 theories of failure, I think, for ductile material. One of them was the von Mises or distortion energy theory of failure, von Mises stress theory. And the other one was Tresca criteria, von Mises criteria, Tresca criteria. So for ductile material, both of these are acceptable, but we can easily generate the von Mises stress, plot the von Mises stress on the screen, and make sure that, assuming that you trust those numbers, because remember, you're not doing any mesh conversion study, so how can you trust it? But let's pretend that you have a fine enough mesh so that you can trust it. As long as that stays below the yield strength, the material design is safe. Of course, you have to use a factor of safety also. Okay, so that's why they reduce the yield strength by the factor of safety. For example, to ensure that things don't go crazy, you take the yield strength, take only half of it, and make sure the von Mises stress is below half of the yield strength. Okay. Now, I will come and do now I told you that this is not the best way of doing the problem. In fact, it's not the most efficient way of doing problem. For example, if you had a structure like that and you took each one of these to be one of these, for example, rods, these are I-beams, of course, then you end up with a zillion elements. So in things like that, we need to use a more effective approach, and namely use a beam element. Beam element, you put it on the wire frame, but you define the cross section. You say the cross section of these beam elements are circular with a given dimension, and then you do the problem. Okay. Well, that's next week. All right. So let me go ahead and do this problem. First things first. So you go to CATIA. When you start CATIA, immediately the way it's set up here is that a product file comes up. Now, I suggest for now that we are not using assemblies, let's close this thing and start with a part file. What is that? Part file. Okay. And I know I haven't done anything, but right away I'm going to save this thing. File, save management, save as. On my desktop, I create a new folder, and I put here, okay, lecture 1. How about that? Lecture 1. Okay, good. So I created a folder. I'm going to put this part in there. And later on, when I create another file, which is called the analysis file, I'm going to put in there. Because this is very important to organize your work. Because on the midterm and on the final exam, you'll be given 4 or 5 problems, okay, 3 hours. And then each one of these problems should go in its own folder. In it, you have several files, and then you upload this file, this folder, into the location that's reserved for you and you only in the Y drive. So do not put everything in the same folder, problem 1, problem 2, problem 3. All of these will have parts, will have maybe products, etc. We have analysis file. Do not put them all in the same location, because in all likelihood, you're going to really mess it up. Okay, good. Now, I'm going to change my units here. So tools, options. For units, I'm going to go to length, is already in inches. That's good. And I'm going to go to, let's see now, density. Well, you can leave it like that, but really the density, depending on what units if you're using inches and pound, the density is this guy called, let me see now, pound per cubic inch. Yeah, okay, so we can do that. Or slinch per cubic inch. This right here, slinch per cubic inch. I'm just telling you, if you're using inches, what is the thing that's consistent? Okay, so inch, slinch, per cubic inch, and mass is actually slinged. This is slinged, okay? What else do we need? Let's go scroll down here. We have pressure. We don't want Pascal. We want PSI, right? PSI. And I'm sure when you use the version that's installed at the university, there is also something called stress. You may not have pressure, you may have stress, and then you're going to change it to PSI. But this is good for me. It was already there. Now, what I'm going to do is to create this model. I'm going to create a circle and this center curve in two different sketches, and then say, okay, rip this circle along that center curve. So let's see now, the dimension radius of cross section is 1, and this is 8, 5, and 1. So let's go ahead and do that. Why don't we do the cross section of the thing first? So on this plane, I will sketch. Let's see, draw a circle here. This was on the XY plane, as you can see, and I'm going to dimension it. Radius was 1, and exit. Good. So this is the sketch that I created. This is the profile, and then I'm going to make another sketch in that vertical plane. So on that vertical plane, which is YZ plane, I'm going to sketch a profile, center curve. Oh, it's the wrong one. Let me delete this. I took this line. I want the profile right there. Good. Let's dimension these. So the dimension from this point to that line is 8 inches. 8 inches. And I believe that thing was 5. So the dimension between this point and that is 5. And what else we have? The radius of that fillet, the radius of that bend is 1 inch also. So there is your 1. Good. Exit. Okay. Now, I want to, in other software, they call it sweep. Sweep this circular profile along that. CATIA does not call it sweep, it calls it rip. See, path directly goes up. But if you want to go along a path, curved path, you say rip. And read it carefully. It says profile is that circle. Center curve is that sketch. Yeah, keep angle means that these are 90 degrees. It's going to be kept perpendicular to that center curve. Good. That is what I have. Okay. There. Now, if you want to change the rendering here so that you can see the edges, let me see. Let me try the, okay, there we are. Good. Now, we have to specify the material. Now, I gave you some values here, but I'm going to use the default properties in the database. You can always go change this. Oh, by the way, I just realized that the loads were 2,000 pounds. I thought that it was, I said, I don't see it. Let's put 1,000. It says here, load is 2,000 pounds. But anyway, so I'm going to take the steel on that part and say, okay. Notice that it puts the properties of steel down here. If you double click on it and select the analysis tab right there, it tells you what are the values that our CATIA database uses for that. For example, look at the Young's modulus. It's 29 times 10 to the 6, almost 29 10 to the 6. And in this problem, I'm saying 30 e to the 6. No problem. If you want, you can change it. However, I'm just telling you I'm just telling you that in future, I will not change material properties. I will use the database properties, okay? It says, okay, the Poisson ratio is 0.3. The default value is 0.266. I'm going to change this into 0.3. And I don't need these things. And there is also a yield strength here. That's totally, just for your own convenience. This is not correct because the yield strength of the material depends on its heat treatment. Okay, yield strength of structural steel is about 30,000 psi, like that. But for something that's used in a destroyer or a submarine, it goes up to 100,000 psi. So anyway, this number is never used. Okay, this number is there; it's never used. If you want, you can change it. It's never used. Okay, good. Let's click on the floppy here so that whatever I had in that folder, it's saved. Now we're going to go to generative structure analysis. You see that? For you, if you start menu, I've customized things here so that, when you go to the lab, you don't see these things like that. You start from here because I've customized it so that the stuff that I use regularly are way on the top, okay? But anyway, if in your case, you go to analysis and simulation, generative structure analysis, analysis and simulation, generative structure analysis. And it says, do you want to do static analysis? Yes, we do a little bit of dynamic later on, but not at the beginning of the course, okay? So we say, okay. Now notice that first of all, the color has changed. That's because you put material on it. If you don't like it, let's go and put the boring material, boring shading on it right there. Now it created a mesh for us. It divided this geometry into bits and pieces like that. And if you first of all double click on this, it says it's using parabolic. If you want, you can use linear. Let me actually use linear, okay? And then the size, it says default size of 0.56. It looks at the overall dimension and comes up with this. You can change this. Just look right now. Just look right now. It looks like this roughly. I can go and change this thing. I'm going to make it 0.2 or 0.2, okay? And then look, it's a lot smaller. If you make this thing too small, you're going to sit there for a long time before this thing completes. That's why I'm actually going to make this thing a little bit bigger, 0.3 linear. Now, you want to see your mesh? You put the cursor on nodes and elements. You put the cursor there, right-click, mesh visualization. This is a warning that it gives you. It says, hey, this may take some time in case you put inadvertently a micron. So we say, yeah, I know. But there we are, right there. So this object is broken into little pieces. Now, to do the rest of the problem, I'm going to deactivate this. I can delete it, but it's better to deactivate it because in real life, when you delete the mesh, it takes time for it to get regenerated. But I just deactivate it. Put the cursor there, right-click, deactivate. Good. Let's do the rest of the problem. The rest of the problem is this bottom is clamped. So under the restraints toolbar, see that? Restraints toolbar. You click on the clamp. You select that, say, face. You can do the edge, but you're solving a different problem. I'm telling you, in this problem, I want the face to be clamped. If you put the clamp on the edge, it'll take it, but you're not solving the same problem, okay? It may be close to the same problem as long as you go away from that support, but you're not solving the same problem. Good. Now the load is 2000 in this direction. So look at the load toolbar, so restraint toolbar, we already did. Put the clamp there. Loads toolbar right there. You click on, I don't have a pressure, this is pressure. This is other stuff. This is a force, distributed force. You select that face, and in the right direction, proper direction is direction X minus 2000. And this is, of course, 0. There we are. You see? Zoom in closely. That's what you get. You might say, well, you selected the face. Could I have selected the edge? Yes, you can, but you're solving a different problem. I want this face to be according to my instruction, this face to be loaded with a total force of 2,000 pounds. Total force. Now, if you say, okay, what happened, this 2,000 pound, how is it actually acting on this? Now, first of all, this is a mathematical assumption that you're making. This is an assumption that you're making, that this force, I decide to put it on that face. And the way it works, this 2,000 pound, it's if hypothetically there's 2,000 nodes on this face, then this 2,000 pound, it puts 1 pound on each node. If there is 500 nodes on this face, then it puts 4 pounds on each node. So that's when you put a distributed force on a face or an edge, it basically distributes equally among those points. Is that a good strategy? Well, maybe not, maybe yes, depends on the problem. So we say, okay, good. Now, notice that if you go to File Save Management, another file has been created. You already had created this cat part. This was created, but you have to save it. Save as in that same folder. Remember lecture 1, analysis 1, and we say okay. Because at the end of the day, on the final exam day, on the midterm, you have to give us both the part and the analysis. Please do not rename your parts or analysis by the way you rename, for example, a Word file. Right-click, rename, change the name. Do not do that, because CATIA's database will lose track of the information. Okay? And then when it comes us to mark your paper, we see that because you decided to use the right-click, rename, the way you do it in PDF or Word, the link has been lost. Okay, good. Now, so what did we do? We created the geometry. It automatically meshed it for us. Remember, we needed a material. We had to put a material on it. We use restraints. We use loads. You're going to be doing this thing for the next 6 weeks. And then when you're done, you say compute. Compute, right there. It looks like a calculator, but, and say all. And it's done. Now, if you had used a micron as the size of these elements, you would sit here probably a few hours. Okay, that's why you have to be careful. That's why it warns you that, hey, when I generate the mesh, it could be take a while. Now, can I see the deformation? You click on the images, deformation, give me the shape without numbers. And you know that this is what's going to happen. If this is a clamp, you apply a load here, it's going to bend like that, and you can animate it. This strip of film here, right there, right there. There we are. So it looks good. Now, it doesn't tell you much, but if you made any gross errors, some of it may show up here. Now, you want numbers? You click on this icon, displacement. This was deformation, just gave me a change of shape. This is displacement. You click on it, and notice that if you zoom in, you see these arrows. So that node goes in that direction in the XYZ by this amount. And in fact, this is fine. There's nothing wrong with it, except I'm going to change this to, I double clicked on it. And by the way, notice that every time you generate an image, it's done here. It's recorded right there. I generated this, so it deactivated the other automatically. You can double click here or double click on one of these arrows, average ISO, we say okay, and then change the rendering from down here, material shading. There we are. Now, what that means is that all those points, nodes, which are in red, they move by 0.00384 inches. All the nodes that are in this area, the blue one, move anywhere between 0, because the bottom is entirely clamp, and 0.00384. Now, stress, 1 meter stress. You click on it, and this is 20,000 psi. If I trust these numbers, And if I say, okay, the yield strength of the material, I don't know, maybe 34, 35, then this is fine. These things are not going to yield. Okay, couple of things. Notice that you get color, you get numbers, but I have no clue how reliable these numbers are. So the fastest way, at least to have some idea of what's going on, is to go and use a better type of element. See that? Remember here we used element, double click on it. From linear, go to parabolic, more accurate, and run it again. Run it again. Done. Let's activate the von Mises stress. Remember it was 20,000? 28,000. I have no confidence in either the numbers that I got before or these numbers, because it went from 20,000 to 28,000. That's a gigantic drop. This is why people have to do a mesh convergence study. In other words, it's easy to generate good-looking colors and numbers, but are they real or not is a different matter. That doesn't belong right now to this course, okay, right now. We'll talk about these things more in detail. Now, a couple other things. So let me deactivate. Now, when we are done here, I can deactivate any of these plots that I have generated, like that, for example. Now, suppose that this force that I applied right there, this load, I wanted to do that perpendicular to that. So if I double click on this and apply the 2000, not in the direction X as I had, but the direction, for example, Y, it looks like this. And let us run it again. You will see that there is no torsion anymore. If you look at the, for example, deformation or translation, it doesn't matter. Deformation looks like that. Change the rendering here. Change the rendering to this so that you can see it. Now notice that if you look at the view from the front, actually side, view from the side, good. Notice that you can animate, and this thing doesn't go to the left or to the right. In the previous load, it did go to the left or to the right, depending on how you applied your load, but that's why this thing actually, twisted. This one was torsion. But if you apply a load like that, it doesn't go to the side. Now, if you look at, for example, just hypothetically, von Mises stress, let me change the rendering here. Notice that both of these are active. That's why it looks ugly. So deactivate this, therefore deactivate it. There. Now, do you agree with me that everything on the right is symmetric on the left? And think about it for a minute. Yeah. So actually, I didn't have to model this entire part. If the load was like this, I did not have to model that entire part. I could have done only half of it. So symmetry should have been used if the load was like that. Where is that agenda here? Symmetry issues, a big thing in this course. So on the final exam, every single problem will say use all planes of symmetry that apply. In other words, if this was the problem with this loading, do not give us the whole thing. Give us half of it, but there's more to it. You can't just cut it into half and say, hey, here it is, I ran it. There are some issues that you have to watch out. And just to make it clear, there are no part marks for those aspects of the marking scheme. Okay, if you gave us, for example, this problem, just hypothetically, if we gave you this problem and you did not cut it into half, okay, if the problem had 20 marks, in all likelihood, the way it's set up, the marking scheme is you're going to lose about 7 or 8 marks. Okay, something of that order of magnitude. What I'm saying is that some modules, some aspects, there are no part marks for it, period. Please pay attention because these are, I mean, you have 6 weeks to build upon it, but I'm saying these are important. All right, folks, so let me save this thing. And then before I adjourn here, let me also remind you that when you cut this thing, if the load was like that, if you cut it, points on that artificial cut that you created do not go to the left or to the right. They stay on that vertical cut plane. And that's what we call a roller condition. CATIA does not call it roller, it's called surface slider. And that's a fancy way, roller or surface slider is a fancy way of saying that points on that plane do not penetrate it, do not go to the left or to the right, they stay on that plane. That's what we mean by symmetry is a big thing in this course. All right, folks.